All right, so you guys remember how we talked a little bit about some of the properties of a fluid or a liquid this morning? So we're going to continue on that by doing some demos. So this morning we talked about a property called viscosity. Does anybody remember what viscosity is?
It's how, yeah.
Thick. The
Right.
thickness of a liquid.
Right, so it's how we observe how thick or thin a liquid is, right? So just to recall, if a liquid is really thick, is that viscous or is that not viscous?
Not
Viscous? No.
It's viscous.
Viscous.
Right? So the actual definition of viscosity is that it's something that resists its ability to pour. So it's actually because of friction, right? So keep that in mind when we're going to do this demo. So has anybody ever made gingerbread before? Gingerbread cookies? Yes. Okay. So there's one really special ingredient in gingerbread cookies that's responsible for making it really soft and chewy on the inside. Does anybody know what that ingredient is?
Molasses.
It is molasses, yes. So it's molasses.
Whoa.
This is molasses right here, right?
Fancy.
Everybody seen it before? All right. So it's really hard to open all the time. Okay, so I'm going to pour some molasses to start my cookies.
Ooh.
That pours super slowly though, right?
Mm-hmm.
I don't know. I need a lot of molasses. I don't feel like that's pouring quickly enough. Is there any way that you guys think that maybe I can make this go a little bit faster?
Heat it up.
Heat it up? Yeah, sure. We could try that. So, when we're thinking about our particle theory of matter, and we're talking about a liquid, do you guys remember what it looks like?
Particles bouncing around.
Right,
The
yeah.
molecules are like
So-
kind of spread out.
In a solid, molecules are pretty close together. They're usually cross-linked to each other, right? So they're linked really highly. So they tend not to move very much. So if we're going to draw some movement, they kind of just vibrate in place a little bit, right? Like being on a really crowded bus, okay? But in a liquid, these things, these little tiny molecules, can slip and slide past each other, right? Okay, so we're going to try heating up our molasses, and we'll see what happens. So we have one back here that has been sitting on the hot plate for a little while. I'm going to give it a quick stir and pass it around so everybody can feel that it's a little bit warmer. It's not super hot on the bottom, but it's warm enough that you can tell that it's been warmed up. Okay? So we think that this is going to pour quite a bit faster, right? Let's try it out. Much faster, right?
Mm-hmm.
Quite a bit. All right. So that's a good way to affect the viscosity, right? Temperature. So what I would like you guys to do is I want you guys to try to draw me what you think is happening to these particles that it flows faster. What happens when you add heat to those particles? And why does it flow faster? So just draw, you can draw like a quick little diagram, you can write it out if you want, and then just show me your whiteboards, and we'll take a look. Awesome. Okay, so I see a lot of drawings where things are kind of moving farther out, right? So when we're adding heat to something, what does it add to the particles that are in that substance?
Energy.
Energy, right. And so when we add energy to molecules, what happens?
Move faster.
They move faster, right? So when we have molecules that are moving faster, they're going to be able to slip and slide past each other faster, right? Which ends up resulting in us being able to pour something a lot faster, right? Okay, so that was number one. Now, as kind of an extrapolation of this, I don't have an experiment actually set up for it, but what do you guys think might happen if we cooled this instead?
It would be more viscous
More viscous. Why?
because the molecules would be moving slower and not apart, I guess.
Right, and why are they moving slower? What are we taking away from our little equilibrium here in this container? What are we doing to it?
Energy.
Right, we're removing energy from it. So the molecules start to move slower because they have less energy. So they slow down, becomes more viscous, right? Exactly. That's totally what happens. Okay, so we're going to take that. Oh, and I splashed everywhere. Sorry. And we're going to talk about another liquid. Okay? So this one's a little bit different. So this one is what happens when we mix water with a certain type of powder. Okay? Cornstarch. Everybody's used this at home before, maybe?
Mm-hmm.
Yeah, it's coming up to the time of year when we actually use this quite a bit, especially in baking and stuff. Can anybody think of any real-life applications that we use starch in?
Shortbread cookies.
Shortbread
I make
cookies?
them all the time.
Sure. What else? What else is really important? It's coming up next weekend. A lot of people...
Thanksgiving.
Yeah, Thanksgiving. What do a lot of people eat at Thanksgiving?
Stuffing.
Turkey.
Stuffing? Yep. What do they eat that has cornstarch in it, maybe?
Pudding.
Puddings, maybe?
Gravy.
Gravy. Also pie. If you like cherry pie, it's a great way to help make cherry pie, right? So, cornstarch. We use it a lot. It's in a lot of things, but we don't really know that it's there, right? So, I'm going to pass it around. Everybody can take a quick look at it. You can waft it a little bit, see what it smells like. Just try not to inhale too much of it. All right. So, I'm going to hold this up. Everybody can see that a little?
Mhm.
Yeah? So what does that look like to you guys?
Milk.
Kind of looks like milk, right?
Thick old milk.
Does it look like thick old milk? Yeah. So this is actually just water and cornstarch mixed together, right? So it looks kind of liquidy, pretty runny, right? Does that look like a liquid or a solid? Does it look like it's viscous or not very
It's almost
viscous?
almost jelly looking.
Jelly looking? I don't know. Does that
Looks
look viscous or not viscous to you guys?
Not viscous.
Not viscous,
no.
right? It looks pretty runny, right? But what happens? Do you guys think I'll be able to pick this up?
No.
No? Let's see.
Depends how fast you
Ugh.
It's a little liquidy, right? What's happening? What if I squeeze it? What do you guys think might happen if I squeeze it?
it gets thicker.
It gets thicker, right? Right? So I'm going to have a volunteer come up here who doesn't mind getting their hand wet, or I could do it if nobody wants to
I'll do it.
volunteer. Okay. Okay, cool. So you are going to take your fist and punch down into the liquid as fast as you can, then pull your hand out right away. But yeah.
Oh.
Is that not quite it?
Try faster.
Oh.
Just punch it.
Punch.
Pull it out.
There you go. Close. It's a messy experiment, right?
Yeah.
I have wet wipes just over there if you would like one.
Okay, thank you.
So once you've just punched it, it acted like a liquid, right? And went all the way over the container and splashed a little bit. But the area where he actually punched, his hand got stuck, right? Why do you guys think that happened?
You like pushed all the molecules together or something.
Yes, that is very, very close. So what happens when we mix cornstarch and water together is that the solid particles are so fine that they actually stay suspended in the liquid. So it's not really a liquid and it's not really a salt. It's kind of like a hybrid of the two. So what I'd like you guys to do is try drawing me a picture of what you think this liquid looks like, or this fluid looks like.
This is the liquid. I need your marker.
Liquid?
That's liquid. And then this
You
is
might need another color. You can borrow a color from your neighbor if you'd like.
this is the cornstarch.
Right, okay. So now what happens when I push down on it, it's quite solid, right? So, like Parker mentioned, what happens when we put our hand in it is the force downward pushes all of those liquid molecules out of the way over to the sides. So that's why we ended up with that little tsunami of liquid coming out the side, and it was more solid right in the center. So if you do it really fast, I can kind of show you guys. Like it's like trying to punch into a wall. Like it's pretty solid, right? Unless you stop. And then there's no pressure being exerted down, right? Instead it exerts on the side. So now that you've seen this liquid, Can anybody think of maybe somewhere that you've seen this in real life? You might not have seen it in person, but it's something that can sometimes happen on, like if you're going on a wildlife trip, if you're going on a nature walk or something like that.
When I step in mud.
Mud, yeah.
Mud, yep. Even more specific than mud, though. There's a very specific type.
Swamp.
Something that you'd find in a swamp.
Quicksand.
Quicksand,
Oh,
exactly. So quicksand works this exact same way. So what happens is the viscosity actually changes depending on the force that's exerted on it. So if you have a force that's coming in towards the top, it acts more like a solid, right? So that's kind of the way it works. All right. Well, now you guys have seen that, so we're going to try some more stuff with viscosity at your lab benches. A little more messy than I thought.
Sorry.